Good morning, Jan.
Hello, good morning, Frederic.
Can you hear me?
Yes, I can.
Sorry,
You
I
too?
can't hear you.
You can hear me?
All right, I can't hear you, Jan,
Really?
for some reason.
Okay, so it's strange. It should work.
You activate your microphone?
Yes, yes, yes. Is it better now? Strange. Can you hear me now?
Jan, we can hear you. Maybe she has problem.
So if the others can hear me, then Fred, there is something on your side, it seems.
Yes, it's solved.
Okay, great. Perfect.
Yeah, that's
Very
fine.
good. Thank you.
Okay, so it's nice to see you, Jan.
Yes, likewise. How are you?
I'm good, thank you. What
Very
about
good.
you?
I'm fine.
Thanks for accepting this invitation.
Sure, pleasure.
Talk today on the ABO webinars. I think it is 11 and participants are getting connected for most of them. We are missing maybe a couple of them. Just an information before we get started. The way the webinar works so far is based on invitation that we send with the working people at the coast. But we think it would be nice also if people want to volunteer to present their labs or company's activity. And it's something that we plan to propose on the website soon. But in the meantime, if you wish to present what you do, because this course is your tool, this is our tool that we can use to present and to meet together and to present what we do. So if you wish and volunteer to participate to a webinar in the coming weeks or months, just send me an email, and then we will discuss this possibility and slots, available slots, and so on. And then it would also facilitate our work, because you won't have to review every participant of the course and make choice. Then you can volunteer. I think it's it seems that we have interferences on the network right now. That was the main information today. So today we are very happy to hear Jan Mačák. He's from the University of Niche, if I pronounce okay, in Czech Republic. Jan is a very accomplished senior researcher and group leader in his university, with already a very impressive career and very impressive awards and grants, such as the prestigious ERC starting grant. Very interestingly, also Jan works on the IO2 nanotube layers. And one more information, Jan is the only speaker today, so we have plenty of time. And so please feel free to tell us about the nice research you do in your lab. Thank you.
All right, great. Thanks, Frederic, for this beautiful introduction. I do appreciate the invitation, and I'm glad to be here with you today. So thanks for joining. And in about next 45, 50 minutes, I will try to entertain you with the story of the titanium nanotubes bioionization, because I was there from the relatively very beginning, and throughout all my research career, I actually spent significant efforts in developing this material. So before I start, I wonder, can you see my screen?
Yes.
Yeah.
Very good. Perfect. So let me just use the laser pointer. So as Frederic said, I'm coming from Czech Republic, University of Pardubice. I also work at the Brno University of Technology. And just to show you, Pardubice city is in the middle of Czech Republic. Brno is here, close to Vienna. Both institutes I work for are well-renowned materials research institutes, and we have, of course, necessary equipment for the agenda we are doing. And today I will be talking about material which has official name self-organized titanium dioxide nanotubes or nanotube layers, but we can just shortly call it titanium nanotubes. And in the first part of the lecture, I will discuss how we make them and how we make different diameters and thicknesses of these layers. And I will also discuss what are their properties. And in the second part, I will focus on applications, and I will especially discuss with you the photocatalysis, which is the ultimative, let's say, application of titanium dioxide. So just maybe a little bit of reasoning at the beginning, why we actually deal with TiO2. I think it's a fascinating material that has many properties and lots of functions, actually. So first of all, it can clean itself upon illumination of UV light. I'll get to that in the second part of the talk. So it has a tendency to clean its surface, which is interesting. It can change, for instance, its wetting properties depending on the illumination. It is highly biocompatible. So all titanium implants that are there in bodies, in teeth, and so on, have TiO2 surfaces. And last but not least, it's also nominally a very white, bright material with high refractive index. And some of these properties are based on semiconductive nature of TiO2, especially of the crystalline forms like anatase and rutile. And obviously, as for many other materials, like with carbon, it's the same. We have many different structures available. So you can, in principle, have flat layers. You can have titanium nanoparticles. You can have nanorods, nanowires. But we are focused on nanotubes. And the reason for that is that we find them especially interesting because they are like 1D, one-dimensional nanomaterial, which has high surface area, also high surface to volume ratio. They have tunable dimensions, so we can, in the meantime, play very well with especially the nanotube diameter and nanotube thicknesses. And similar to porous alumina, they have some empty space, which one can use as templates and scaffolds. So there are many different reasons why to deal with nanotubes. And compared to some other techniques that are there, like hydrothermal soldier techniques, I come from the electrochemical background. So my interest is always to use electrochemistry. And in the slides that I will be presenting today, actually a lot of it is about electrochemistry. So I just want to start with the simple scheme of a beaker in which we actually realize most of our experiments. And we have an anode here, which is a piece of titanium. And we have a cathode, which is, for instance, platinum. And we connect these together, apply voltage here, and we have here a suitable electrolyte. And when we do this, so when we oxidize the titanium, we have an oxide growth on its surface. So we are virtually growing titanium dioxide. And by doing so, we are, of course, changing the property of the anode, and we are giving a completely new surface to it. And the reason why we do it by electrochemistry is not random. There have been two great examples of materials from past, so let's say from older times, and these are porous silicon and porous alumina, which are these fascinating structures. So this is porous silicon, porous alumina. As you can see, these are super well ordered. I think they look really amazing. Structures which have defined pore geometry, defined especially pore, which can be tuned by electrochemical conditions. And these have been great inspiration for researchers to conduct something similar with titanium dioxide. So the titanium nanotubes actually are the youngest member of this family. We grow them by anodization of titanium, as I said. And in the next few slides, I just want to be a little bit more detailed about how it works. So when you do it the way I just showed in the beaker, and you apply some 10, 20, 30 volts in conventional electrolytes like sulfuric acid, for instance, you will do nothing else than just thicken the oxide, because there is always native oxide, which you will just grow thicker. And the thickness of this oxide will be proportional to the applied voltage. This is very well-known mechanism of oxidation, which follows so-called high-field ionization. And a completely different situation will occur when you add fluorides into these electrolytes. So, for instance, when you take HF sulfuric acid or ammonium fluoride and ammonium sulfate, a new situation will occur. And if you do everything well and you apply the right voltage, the right concentration of fluorides, you will end up with these self-organized titanium nanotubes. In the early literature, which comes even from already 1984, researchers use HF electrolytes. However, after the like 20 years later, 30 years later, people realize that HF is not really good, not just for security reasons, but also because it's very acidic and it etches these tubes relatively quickly. So you can make them in HF. On the other hand, if you don't rinse it quickly, if you don't wash it properly, you can have some etching of these. So HF is not so good, but in principle, it helps you to grow the tubes more or less following this scenario. So what happens on the very surface of titanium is that you have this native oxide. As you apply the voltage, as the time goes on, there is some kind of, we could call it corrosion. So the fluorides actually penetrate to the titanium and they actually dissolve the titanium. In the same time, the just dissolved or etched parts are also oxidized. So there are some pores grown, and in the course of time, what happens is that the large pores become even larger. The weak pores actually die, and it's always like a natural competition, like in the nature. So stronger survive, younger die, and at the end there is this natural self-organization phenomena, which makes the tubes arranged more or less in the same fashion, so that each tube occupies more or less the same area. So this is also the status of the energy which has the lowest entropy. And so this takes about 1 hour, 2 hours. And if you really want to get rid of HF and if you really want to understand the process, you have to try to understand the growth in really, really good details. And that's actually what we did. Here you have again the scheme of how the tube grows. You have to understand also of what happens here at the bottom of each particular tube, because there are of course some reactions. There is some diffusion of the fluorides inwards. There is some oxygen diffusion also, and there is also some TI4 migration. So once you understand this equilibrium between the etching and oxidation, you are able to come up with something which looks like this. So you realize that after a few hours of ionization in HF, you get a limiting thickness and you can't get thicker, no matter how long you analyze. So one of the key successes or one of the key steps in this material and in its development was the transition from HF electrolytes to actually fluoric salts. And the idea was to significantly enhance the tube growth, but to slow down the dissolution. And it is about already 17 years ago when in the lab of Professor Patrick Schmuckli, we were fortunate to find out suitable electrolytes, which were based on fluoride salt. So we did not use HF anymore, and we used rather neutral electrolytes. And by doing so, we were able to have the acidity inside the tubes only at the spots where we needed it. So where we needed actually to drill deeper into titanium, but the tube walls were preserved simply by having higher pH there. So the titania did not readily dissolve there as it would dissolve here. But because this was neutral, these walls were preserved, and at the end, the whole nanotube layer could grow thicker. And we showed it first in the aqueous solutions, then we switched to viscous electrolyte, like based on glycerol and ethylene glycol. And there we go. This is like the executive summary of all that. So you see here something which we called generations of tubes. So this is grown in HF, only about half micron. These are completely aqueous solutions with ammonium fluoride, glycerol ammonium fluoride, and ethylene glycol ammonium fluoride. And you can see here that through very thin layers and by using different electrolytes, we were able to get very thick, very robust nanotube layers that are actually very cool, because these layers have very high surface area, and they have lots of material at a relatively still small volume. All right, so now 17 years later, we got in the situation that we can relatively comfortably prepare nanotubes with different dimensions. This is similar to porous silicon or porous aluminum. So there are usually these charts, like in the ionization regime, like what voltage you need to apply to get what diameter and what thickness. And this is exactly shown here. So in the meantime, it is possible to prepare nanotubes that have diameter far below 100 nanometers, even like 15, 20 nanometers, but also far above 200 nanometers. So it's pretty broad. If you look at the thickness, there is some dependency to the diameter. So in principle, when you want to grow a low diameter, you have to apply rather a low voltage. And this means that the layers will be rather thin. In contrary, if you apply rather high voltage, most likely you will end up with rather larger diameter and thick layers. So this ellipsis shows some kind of optimal region where if you take the recipe, normally even a beginner should be able to reproduce it and make these tubes. The areas outside the ellipsis are a little bit more difficult. You need to do some development there and eventually some additional things like cooling of the electrolytes and things like this. So this is the executive summary of the dimensions that are feasible these days, especially in the range of 100 to 200 nanometers. There's lots of options for making tubes from 1 to several hundreds of micrometers. And I'm actually very proud that recently we have achieved, I would say, a significant milestone in the synthesis of the tubes in short time. Because if you want to grow really thick tubes, which are typically the most useful for many applications, you need it normally many hours, like 12 hours, 24 hours. And especially with the costs of energy these days, it would make sense to make this process much shorter. And we were able to actually do it by adding lactic acid into the electrolyte. Again, the pioneering work was shown on that by the Schmuckis group, but we have taken this and made much deeper investigation, and we have tried to use also different concentrations of the lactic acid. And the beauty about it is that the lactic acid prevents the electric breakdown, which normally occurs when you apply too high voltage. So to make it very clear for you, for instance, if you apply 100 volts, most likely this will be too much. And what will happen is that you will have some avalanche increase of current, the electrolyte will heat up, and at the end you will have something which is called breakdown. So the layers will lift off and everything will be damaged. And that's of course no way to go. But if you do insert lactic acid in the electrolyte, you can actually go much higher with the voltage. So you can apply, for instance, 140, 160 volts, which is quite a lot. But this gives you extremely high currents that you can maintain for a relatively short time. So in principle, suddenly by using high voltage, you can anodize only 15 minutes or even less, and you have, as you can see here, almost 80 microns, if even more. So this is great because this is completely new. This was not possible a few years ago to make such thick layers in such a short time. And of course, it makes the preparation of the tubes, and especially if you need more samples, very effective. Plus, it has some environmental and energy aspects because we don't consume so much electricity. So this is one of the highlights. And I'd like to continue with discussing some additional features of the tubes. So as we learned, we can adjust the dimensions, right? Because we can apply different voltages. So we have diameters, walls, and lengths different. We can also adjust the ordering. I will get to that in a minute. And what is also important is that these tubes are normally very well adhering to the substrate, the titanium underneath. But there are tricks how to separate it. So actually you can make really freestanding nanotube layers or membranes or whatever. And this can be very handy for some applications. And as I said, also already when I discussed the templates, there is a huge internal space as well as there is some gaps between the tubes. So you can use this. I will not talk about it today because I usually keep talking about it. So today I will really focus on the tubes themselves, but it is possible and I would like you to know. So for those who are not yet necessarily familiar with this material, so titanium nanotubes always grow amorphous. So when you do the anodization, no matter what you do, you will have always amorphous structures. So if you do XRDTM, you see no crystals. If you anneal it in air, you can also take other atmospheres, but typically air, it's the easiest. You will get, depending on the temperature, anatase or rutiles, or mixture of anatase and rutile, right? So you can see you have this typical 101 anatase structure. And in terms of composition, if you do XPS, you will find out that you have always, of course, titanium dioxide. You might also have some carbon and also some fluorine. And the carbon actually comes from the impurities from the electrolyte, because the electrolytes are typically carbonaceous, like ethylene glycol. And the fluorine comes from some traces of the ammonium fluoride. And but it's possible to get rid of it. So just before I go farther, I want to show something which is frequently overlooked, and not many people pay attention to it, but it's kind of important. And that is something which is related to availability of materials. Like if we buy titanium in Europe, it is probably different titanium than in China or America or Russia. And for this material to be really reproducible in terms of synthesis, it is important to look at what happens when you take different titaniums in terms of the tube morphology and dimensions. I can already tell you that the good news is that not much happens. This technique is so universal that in principle, no matter what titanium you take, and also almost no matter what purity you take, it still has to be, of course, the majority titanium, you will have tubes at the end. And you can see here these EBSD patterns which show you the grains. So of course, every titanium from every supplier has slightly different grain structure. The grains have different orientation, different size, but nevertheless, we looked at it in details and we found out that there are always tubes growing on every single grain. We did some inspection by really proper EBSD and TM analysis on grains with different orientation. And there are on the surface definitely grains with very different orientation. And the good news is that the tubes still grow. So in principle, it's absolutely not depending on the grain orientation or on the grain size. Just last information about the substrate. Also, you might have single crystalline titanium or nanocrystalline titanium, and the good news is that the tubes also grow on these substrates. So basically, this polycrystalline titanium foil is the most typical substrate that you take. I would say 99% of cases is this substrate, but sometimes you want to take thicker sheet or single crystalline sheet. No matter what you do, if you use the standard conditions, the diameter and the thickness will be more or less the same. Now, to those of you who know porous alumina, you probably are very well aware of the fact that this material is not just extremely fancy, but also extremely beautiful when you look at it. It's really pleasing to see these honeycomb, extraordinarily ordered structures. And naturally, when we got some knowledge in this material, we wanted to achieve also ordering with the tubes. So I'm sorry that I'm sometimes showing you some rather older papers, but for the story, I'd like to say it and also remind it. So in the alumina case, there are significant papers showing that if you do something like, for instance, repetitive anodization, you can improve the ordering. And it works really almost perfectly for porous alumina. There are not just works by Japanese, but also by, for instance, Professor Marshall, who is the leader of the cost, but also other fellas in the field. You can actually make really nicely ordered structures of porous alumina by repetitive anodization. And we did the same. So we grew up first on titanium tubes, which are somehow ordered, but of course, far from being perfectly ordered. Also, if you look at the bottom parts by SCM, you see that the tubes are kind of hexagonal, but sometimes there are defects. They're like pentagons or heptagons. So it's not really yet there, but if you remove the layer by etching or by removing it somehow, you can have these dimples in the titanium surface imprinted. And then when you continue the same thing, you can actually get much higher degree of ordering. So you see you have more or less ideal hexagonal packing of the tubes. Everywhere there is not really big defects. And this is important because such arrangement would offer some new opportunities like in optical applications, like waveguides and things like this. And it doesn't look ordered only at the bottom here, but it really looks ordered also at the very top. And I think it wouldn't be scientists if they wouldn't try to make it even better. So recently, like years ago, there were some efforts how to, for instance, do some imprinting in the titanium using nano indentation or iron-pit lithography. So you can actually take a mold with a certain distance, you can imprint some holes in the titanium, and then you can, for a short time, otherwise, of course, the imprinted holes will be visible there. But you can see that still the surface is not very perfect at the surface. It looks good at the bottom, but not yet at the surface. What we tried in my team, and I think so far this hasn't been beaten, is to use some kind of protective layer, which we then pattern. So we took titanium, we did titanium nitride coating on it by atomic layer deposition. And we basically created a very thin and very robust, chemically and mechanically robust layer. And then we took focused ion beam and we drilled holes in certain hexagonal arrangement as shown here. We also varied the distance and the diameter of it. And then we anodized it. So using the pre-drilled holes. And it was actually amazing to see how the holes were perfect, first of all. And second, how this area, which was patterned, really remained in the same patterned way also underneath the titanium nitride layer. So here is the interface of pattern on patterned surface, and you can see the huge difference. So at the end, we tried different distances, different distances between the holes, different concentrations, and we ended up with something which looks like this. So we got not just extremely ordered tubes at the bottom, but really almost perfect excellent arrangement of the tubes at the top. And there is still this titanium nitride layer, which is 3 nanometers thick, but it doesn't really bother us. It doesn't change so much. And you can also see throughout the layer thickness that it is really nicely homogeneous here, some 4 images. So looks great, right? Okay. So let's go on. Just a few information about additional shapes. So for those who are familiar with anodization of titanium in ethylene glycol electrolytes, and for those who have tried to vary the voltage and so on, you know probably that you can do different things. You can create double layers, multi-layers. So if you interrupt your anodization and then start again, basically a new layer will be grown. This is what is shown here. You can also modulate the potential, and you can then do some nanolayers or bamboo-like structures. You can also do rapid breakdown structures, which are very specific cases of the tubes. Let's look at the most typical tubes that are grown in ethylene glycol. And these tubes, when you're looking very carefully, usually have inside, especially at the bottom part, some porous layer inside. You know? It has been overlooked for a while, but then people found out, and then it created some attention. And actually, it turned out that this inner porous wall is TiO2, which has lots of carbon. So it's basically contamination from the electrolyte. And if you do etching, you can actually remove it, and the rather pure TiO2 stays there as before. And we have actually taken this approach and moved it even farther, and we have over-etched these materials, and we were able to disconnect completely the tubes from the substrate, but also disconnect them from each other. So we were able to do, for the first time, actually powders, nanotubular powders. And you can ask yourself, why in the hell you make from these organized tubes so messy powders? In principle, the question would be quite justified. But on the other hand, by doing this, we even further increase the surface area of the tubes, and we make their handling, in some cases, possible, yeah, because there are applications where we would need rather single tubes or tube powders rather than layers. So it makes sense. And I just want to show you some more evidence here. So this is typical example of the double wall structure. So you see the porous wall, that is etched actually the outer wall, and after etching everything's clean. This double wall structure has some implication on the photocurrents, because we shouldn't forget the output is a semiconductor. So if you do photocurrent measurements, you will see that the single walls actually achieve usually slightly higher photocurrent density than the double walls, because there is simply more pure TiO2 overall than with the double wall morphology. Also the onset, so the speed with which the photocurrent reacts is faster. And this applies also for tubes of different thicknesses. Here, just few words about the single tubes. They have been attractive very much, in my view, also in the view of audience that uses these powders, because we were in principle doing this first for biomedical people who wanted to try to see some drug deliveries, like use these tubes as drug carriers or nanorobots. So we tried to do these single tubes, and we also managed to decorate them with super magnetic nanoparticles. And so we grew tubes, etched the tubes to have powders, and then we did the Salvatore reaction to make magnetic nanoparticles on the surface. We managed that. As you can see here in the TM, we have these nice super magnetic particles, which are like on the scale of 10 nanometers. And this gives you incredible power of having high surface area TiO2 in the nanotubular shape on one hand side. On the other hand side, it gives you the magnetic force. So you can actually move these powders in a magnetic field very easily. I just want to say that we, at the first glance, tested it for photocatalysis with the single tube, double wall, and so on. And we investigate something which at the end was not surprising. So the key thing that I would like to highlight here is that the single tubes, really, when they're separated, have the best performance compared to the single wall and double wall tube. So there is something in it when I say that we have even more surface area with the single tube powders. When you decorate with the nanoparticles of magnetite, they are obviously shaded, so the performance goes a bit lower. But the message that I'd like to say here is that by this time, it is possible to make tubes as such, tubes which are super pure, so a little bit etched, and also nanotube powders. These powders were in our attention recently, and we have tried to anneal them at different temperatures, and we have tried to look at the crystalline structure. And I'm very proud to say that we realized that we are the only group in the world that so far achieved to have pure anatase of TiO2 at 7, but even 800 degrees. Imagine, and it's really amazing. Usually at such temperature, you always have rutile or mixture of anatase and rutile, but we were able to clearly show that we have just anatase. This can be quite handy. We will see where we have the paper just submitted on this. So this is quite interesting from my point of view. You don't find anatase at this temperature materials. Okay, so to move to the second part of my talk, a bit shorter, I'll speak about photocatalysis, because I think this is industrially and technologically so far the most important and relevant process that actually is really one material in it. And the process of photocatalysis is schematically demonstrated here. So you have a TiO2 surface, and you have a surrounding area like atmosphere, but it can be also a solution, for instance. And what happens here that when you have a UV light coming on the surface, there is excitation of the electrons from the valence band to the conduction band. And so this is really semiconductor physics, and there are some things that happen here. So there are some positively charged holes that have tendency to travel to the surface. And then they actually react with the water. They're making this super hydroxyl radical. It's a radical with very high oxidizing power. And similarly, the electrons also can oxidize oxygen to this superoxide anion. And both these species have extremely high oxidative power. So they can actually decompose any organic compound you can imagine, up to almost simple inorganic products like CO2 and water. So basically, this is used widely for decades already in wastewater cleaning, air purification, especially like in hospitals, in kindergartens. Significantly, this has been used in Japan, but I think it spread out worldwide. It is also possible to kill bacteria and viruses. So if you have surface of titania that has viruses and bacteria on it, if you shine light for a while, they will be killed. So this can be quite handy, especially after this crazy virus period we have behind us. Hopefully, it is quite nice to know that there are materials that could kill effectively viruses. And this here is a slide showing some pioneering study we made some time ago. And it was a pioneering study where we showed comparison of the photocatalytic performance of tubes compared to nanoparticles. So the photocatalytic experiment is actually shown here. Usually you do in some kind of model dye. So it has a color, and upon the photocatalytic reaction, the color is removed. So it becomes actually transparent. And you measure by UV phase spectrophotometry the color of the dye in time of the photocatalytic reaction. And when doing so, you actually measure the decay of the dye. And when you do the comparison with the particles and tubes, you end up actually with a finding that the tubes do better than particles, which is sad for the nanoparticulate people, but good for the nanotube guys, because in principle, it tells you that if you take nanoparticulate layers like P25 compacted into the same thicknesses of the tubes, there is always slightly higher chance for photocatalysis to be better on the tubes, probably because of the opening of the tubes and higher surface area available, and also diffusionality aspects play a role. So this is just a drawing what happens with the blue dye in time. It gets faster decolored with the tubes than with the particles. It is also possible to use the tubes when you do the etching and you open them as a flow-through membrane, right? So you can actually have interesting flow-through application, and we showed this in this pioneering paper. I was always asking myself if the tubes can get wet inside, and if they really do get wet. And I can tell you that we have some proofs for it, because we have done some electrodeposition, and we always got the material growing inside the tube. So this means that the tubes are really wetted. So that's good. And this brought us to the, let's say, last information that I want to convey today. And that is another challenging task. And that is making the tubes on a large area. And I mean really like not square centimeters, but if possible, square meters. Because we just learned that the tubes have very good photocatalytic rates, but it's not just that, they're actually very good in many other things. And therefore, it would be handy to have these tubes grown on titanium of substantially larger area than 1 square centimeter. But this is similarly high challenge as with the shortening of the ionization. Remember the lactic acid. So that for me, this is the same importance, because we really push the limits of the technology here, and we show what is possible, and we try to really step over the boundaries and push the boundaries. So about 4 years ago, we were able to achieve by proper management of the ionization, so cooling of the electrolyte, and using the right electrolyte also to grow 50 square centimeters. This was that time the record. And we are trying to beat it ourselves, and we can now make these nanotube layers on 50 square centimeters. This opens door for completely different type of experiments that would not be possible with the small scale. And that is using some ISO standardized measurements, because we have now 50 square centimeters, so we can really go on and put these layers into formatted gas phase reactors. So that's what we did in cooperation with Professor Krysa from the University of Chemistry in Prague, who has this kind of photo setup following this standard. And we tried to degrade different gases. Typically, photocatalytic people work with volatile organic compounds like VOCs. because they are dangerous. They are released in households from furniture, from carpets, from many different products. And there are some limits for them, especially for kids, they can be dangerous. So typically you work with hexane, benzene, things like this. And we were again very happy to see that the tubes did the composition faster than P25. Once more, we compared here same thicknesses to compare apples and apples. And recently, on efforts of my colleague Hannah, Dr. Hannah Sofa, she actually was able to grow really, really nicely thick layers on titanium of this 50 square centimeter with different dimensions. So this is absolutely very recent. And look at the thicknesses. So we were able to get from 1 micron to 7 up to 14 microns. Now we are trying to push the limits even more. And we were actually doing also for the first time some extensive texture analysis, because the amount of tubes is now sufficient to do some texture analysis by the BAT. So we can get some pore volume and so on. And here is the result, probably somehow not surprising. And it says that for hexane and benzene, the thicker the layers, the higher is the decomposition. And we haven't reached, for the thickest layer we used, saturation yet. So this clearly shows us that if we would be able to make these layers even thicker, we would probably have ultimately good unbeatable conversions of these gases. And this all also in relatively short time. So please understand that this is a very standardized experiment done really following some ISO norm. You have to give it some time to saturate it and so on. So these are really good and consistent data that show how the tube thickness influences the photocatalysis, and we are trying to understand this in more details. Last but not least, I want to highlight something that hasn't even been feasible last year or 2 years ago. There are people that can print metals, 3D print metals. I mean, there are many of us that can 3D print polymers. This is much easier, but to print metals, that's a challenge, but it's possible. So we have guys at the Brno University of Technology in Brno who can actually print from titanium powders these meshes. So we asked them to print them, and we were able to anodize them. We had to use some specific approach, which is called bipolar anodization. It is a wireless anodization process that, believe or not, it's possible, because it would be very difficult to connect these meshes somehow to have really uniform placement towards the electrode. So we use this double electrode and bipolar assembly here, and it is possible by doing this assembly to grow nanotubes also on these very meshes. And you can then take these anodized meshes, put them in a reactor in a stack, and have a like really proper UV illuminated reactor. And the catalytic rates actually that we got here are simply outstanding. These are probably the fastest photocatalytic rates we ever have seen, and that clearly shows that if you go from the 2D large area to the 3D area, so condensed area, the macroscopic volume, this is the way to go. So these are actually extremely efficient flow-through photocatalytic reactors that, in my view, are something like the first step of making really efficient cleaners that could be used commercially. With that, I'd like to conclude. So throughout different sections of my talk, I was hopefully able to convince you that we can grow nicely over the nanotube layers of different aspect ratios using different protocols, which are also reproducible because many people use it. These tubes can be actually, they are always double wall, especially in ethylene glycol, and they can be etched to have single wall, or even they can be etched to single tube powders. We can play also with the anodization protocols to make really large area nanotube layers. And obviously there's some interplay between the nanotube dimensions and the photocatalysis. And we haven't reached yet the saturation, but we think that the thicker layers, the better. And most important in terms of the 3D printing was the ability to demonstrate that we can anodize also 3D titanium meshes with photocatalytic cleaners. With that, I'd like to thank all my groups, both my groups actually. The persons highlighted in bold are those that have contributed most to this work. So it's Dr. Hannah Sofa, Dr. Lina Sepulveda, Aliani, she's doing PhD on this, especially on the lactic acid assisted ionization. Of course, the others contributed too, but these are the leaders of the ionization labs. So with that, I'd like to actually thank to the funding agencies and who support us in these activities. And thank you very much for the attention.
Thank you very much, Jan, for this great presentation, and that helped us to have all the background and the stories of the design of these beautiful nanotubes and all the advances that have been realized by your group, and for this great application. It's really nice to see this sort of material in a large scale also, because we know that electrochemistry is a very good way to design pores, whatever, but sometimes it limits the scaling up of production. So it's very, very interesting.
Thank you.
Are there any questions for Jan, please? Anyone has any questions?
Either it was too much or I was too exhaustive. I don't know.
No, I think it was extremely clear.
Really? Okay.
Yeah, presentation was clear. I may have one, but I will go to thing that I know a bit better than electrocatalysis or catalysis, but it's about the two things. Did you explore surface chemistry of the tubes? My first question would be, I will go to the application then. Are they hydrophilic? Is that correct?
Yes, they are extremely hydrophilic. They have many OH groups on surface.
Yeah.
Patients say that there is one OH group per about square nanometer or 1.5 square nanometers. Yeah, so there are really many OH groups. So this is super hydrophilic material as such. Yeah.
Okay. And do you? I think you take advantages of this hydrophilicity, and for your applications. Do you have?
I mean, so for example, these groups are good for the atomic layer deposition. I didn't talk about it today, but we also do many depositions with these tubes where we use them as a substrate for some devices. So these OH groups are very handy for attachment of the coatings, but also they are handy for attachment of some other functional groups or other nanoparticles, for instance. You load these materials by nanoparticles. And in terms of surface chemistry, I didn't show any XPS, but we have, of course, extensive XPS knowledge about these. So there's always TR4 plus. So that for sure there's lots of TR4 plus. Sometimes we see some TR3 plus, especially when you do some reduction of the tubes, because you can electrochemically or chemically reduce the tubes so that they become more black. And then there is lots of TI3 plus inside the tubes as well as on the surface. And there is some fluorides for sure always, because you cannot deny it. This is from the electrolyte. But if you do the etching, as I just discussed it, the are gone. So you have really super pure TiO2. This is a very good question. There are different levels of the purities, and the most pure are the etched tubes.
All right, yeah. And it also, I guess, depends on the initial substrate that you use also.
Yes. But I always use like titanium commercially available, you know, which has like 99.9 or 99.8 titanium. Yeah. The remaining traces in these are usually other metals like zirconium, hafnium, and we don't see these in the tube. So they are usually dissolved, they leak out, you know.
Okay. Okay. That's very interesting. So do you have any interest in tuning this hydrophilicity to more hydrophobic tubes and just play with these? Like
not at the first glance, but if you want, we can discuss it and we can do something together.
Yeah, because I mean, yeah, there are so many things that can be very interesting using this TiO2. You mentioned the encapsulation of magnetic particles,
Yes.
or whatever.
Drugs, because we have lots of space inside, right?
Yeah, you have a very, very interesting available volume for biomedical application. And I was thinking maybe of, it's been explored for implants, dental implants, using this TiO2 to charge with calcium phosphate or whatever. That can be interesting because it's a huge domain of research in bio, those implants and
Indeed.
bone reconstructions and things. And it could be interesting material.
True. I could speak hours about it because I just tackle photocatalysis, but of course there are many applications that
I'm sure you do. It's
implants and so on. So indeed.
Okay.
But if you're interested, we can talk,
Yep. Thanks a lot.
Yeah.
Any question from? Do I have to? I don't see any hand raised, but I think anyone can just start talking. I guess no.
No problem.
So, what? Thank you, Jan.
Thank you very much. Yeah. Thank you
your
so much.
presentation.
Yeah.
And
great.
we know that we meet each other in a very short amount of time.
Exactly.
Next month.
Look
Thanks
forward.
for this meeting. So thank you very much for hosting us, by the way. And
Pleasure.
have a great day.
You too.
I wish
Thank
you all
you.
a great day. Thank you, Jan. Thanks
Thank you,
for
Fred.
your
Thank you for the others for
presentation.
joining.
Very interesting. Bye-bye.
Thank you. Bye-bye.
Thank you.
Bye.